If the electromagnetic wave is some form of a particle which we call as a photon, could we just describe the entire universe as a set of particles? And so this is the question that we'll be trying to answer for today, in which we'll be talking about particle physics. So before we get started, please consider liking and subscribing, and also please check the notes in the description for the notes throughout this entire discussion. So let's just get started with the idea of the particles straight away. So we have already known about certain particles, such as the proton, neutron, electron, which all comes from the atom. There also exists the neutrino, which we obtain from the beta decay. We also got the photon. And also, we also figure out that the electron has its antimatter counterpart, which is called as the positron. But it turns out that all of these has their own antimatter siblings. So these are all the things that we have already observed based on nuclear physics, from atomic physics, and etc. So we could also think about the forces, the fundamental forces, and from the previous videos that we have did from General Physics 1 until General Physics 2, we figure out that there is something which we call as the gravity, and then there is also the electromagnetic force. We also have the nuclear force, which we discussed on the previous video, and also the weak force. And this weak force is the one that is governing beta decay. So this entire thing is the one that we have already discovered, but we haven't truly known if these are the most fundamental particles or even forces. So there's something that we could actually do to think of such forces. Let's think of electron repulsion. So if you know about the electron, because they are charged matter, they should have a repelling force. And so if you actually observe them to have not to have any force, we'll just first assume that the momentum is zero. But then if we actually observe only from one particular point of view, what we observe is that there is an increase in momentum in one direction, which means that there should be a exchange of momentum with something else, but there's nothing here. So maybe you could think of maybe the photon is the one that is moving this guy. So if you think of the photon actually having a momentum, which we know about the h over p equals to lambda, right? So this means that your momentum is the h over lambda, which will later corresponds to this additional momentum that you get from the force. So doing this gives you an idea that actually that this photon here is something which we call as a virtual photon, in which this photon interacts with another particle, thus creating this force. And this is the basis of quantum electrodynamics. And then within quantum electrodynamics, you have something which you call as the Feynman diagram, in which if you have the electron here, and then this is the time, okay? So if these are the electrons, they will exchange energy with each other with a photon, which I will denote as gamma. So now this works for the electromagnetic force. But what about the other forces? And one of the things that we'll be answering here is, what about the nuclear force? The nuclear force. So if we actually try to think very closely, we see that we will say that there is this particle which interacts about 1.5 femtometer, in which this is the range of nuclear force. And we'll be assuming this guy to be traveling at the speed of light. So the amount of time that it will take for this exchange will be 1.5 over the speed of light, which is 3 times 10 to the power of 8. And it turns out that this value is gonna be 5 times 10 to the power negative 24 seconds. So you are able to measure this particle at the range of 5 times 10 to the power negative 24 seconds. And if you use the uncertainty principle, you could state that the change of energy over the change of time must be greater and equal to h bar. And we'll say that your measurement is pretty accurate to the point where you could minimalize this value. So what you would get is that your energy must to be 130 mega electron volt, which will conclude that that the mass would be 130 mega electron volt per second squared. This is the theoretical value of this certain particle, in which we call this as a meson. So searching for this meson particle, what we end up finding was something which we call as the muon. So the muon, or mu, has very similar properties with the electron. So it has negative charge, in which this negative charge value is negative E, or the elementary charge. And then other than that, it has spin of half, the spin is half, and etc. But something that's different about the muon is that it has a mass of 200 times the mass of the electron. And if you compute this value, this is not really the particle that we're looking for. But this is something interesting, is that this muon here, which has the negative charge, actually decays into an electron, and it also produces a neutrino and a antineutrino. So after this discovery of muon, we still try to find what is the meson, and it turns out that this meson is discovered in terms of a pion, and pion is the thing that you observe physically. So the pion has a mass 270 times of the electron, and it comes with three different charges: pi positive, pion negative, and pion neutral. And this pion actually also decays. So this pion decays into a muon as well as a antineutrino. So this discovery of particles makes us think, how do we actually classify such particles? And so the way that you do this is that you normally split this into two different groups: the leptons as well as the hadrons. So the leptons here are the ones which doesn't feel the strong force. So this includes the electron, the muon, as well as the tau, which we haven't really discussed yet, but there's a particle which we call the tau, and also the three neutrinos: neutrino of the electron, neutrino of the muon, and the neutrino of the tau. So each of these has their own antimatter. The antimatter exists, such as the positron, the antineutrino, and etc. And also each have spin of 1 over 2. So they are all fermion. For the hadrons, you can split this into two. So these ones are the ones which feel the strong force, and so it is split into two, which is the meson as well as the baryon. Meson has spin of 1, something like the helium atom, helium-42, in which it is a spin. It should be an integer number. And so helium is one of the examples. So these are bosons. And then what we also have is the baryon. The baryon has spin, not spin 1, but spin integer. But for the baryon has the spin of the odd integer over 2. So something like the proton, the neutron, and etc., which means that these are all fermions. And so And so there's also another category in which I didn't put here, which is the field particles. And why didn't I put in the field particles? This is because the field particles are the one which is interacting with these leptons and hadrons. You don't normally straight away observe the field particles, but you observe it through the interaction with the other particles. So this include the photon, the gluon, the particles for the weak force, which includes W plus, W minus, and Z, and also the graviton, in which we are still trying to figure out what is the property of the graviton. So within this observation here, this gluon here is the one that is determining your strong force, and your WWZ is your weak force. So what we observe here is that there is not a nuclear force here. So what is the nuclear force? The nuclear force is just a part of the strong force. But instead of thinking about the nuclear force, this is what we call as the residue of the strong force. Something like the van der Waals force that we studied when we did molecular bonding, in which it is just a part of the electromagnetic force. Same thing here. So you could set up certain reactions of particles, such as the decay or the fusion of such particles. And so if you want to do these types of reactions, you need to conserve certain things. So what are the things that you need to conserve? First is that in general, you need to conserve energy and momentum. This is in general. But also, you should also conserve your charge, as well as your spin, which is a part of the angular momentum. So technically, if I talk about the conservation of angular momentum, you also talk about the conservation of spin. But apart from that, you would also need to talk about the baryon number, the lepton number, and also strangeness. But strangeness is only covered when we are only talking about EM or strong. We don't talk about the weak force with the strangeness. So what is the baryon number, lepton number, and the strangeness? So first, the baryon number tells you that if it is a baryon, antibaryon, or not. So if it's a baryon, it's 1, antibaryon means it's a -1, and not means it's 0. So it's not a baryon. Same thing with the lepton number, but instead of baryon, you just do it with lepton. So there are certain examples of this. One of the things that I will be discussing is the beta decay. So remember about the beta decay, in which the neutron turns into a proton plus your electron plus your antineutrino. So if we compare the charge, it makes sense. 1 and -1, 0, 0, which will be 0. For the spin, on the left-hand side, you have a spin half. The proton has a spin half, electron has a spin half, and the antineutrino has a spin -half, because it's an anti, which means that you would reverse the spin. So it also turns out that it's also the same. And then we could compare the baryon number. So the baryon was defined to be any particles in which it has a integer spin that is interacting with the strong force, which includes the neutron and the proton. So it has 1 and a 1, but then the electron and the antineutrino are not baryon, so they are both 0, which means they are the same. And for the leptons, the proton and the neutron are not leptons, but the electron is, and the antineutrino is an anti-lepton. And so it all balanced out. Lastly, what we have is the strangeness. And the strangeness is something that you mostly observe with bigger particles. So these particles have such things called strangeness, in which it is a integer, and it is theorized that its value range from -3 until 3. So So the strangeness is conserved for anything that is not related to the weak force. So what I want to talk about is about the symmetry now. So everything that we do in physics has symmetry, in which if you do a measurement in one direction, it should be the same thing in the other direction. Such as time, if you flip your time, it should be the same physics. If you flip your positions, it should be the same thing. If you flip your angle, it should be the same thing. But it turns out that when you deal with a weak force, it turns out that you don't have this type of property. And so let me show you one type of an example. Let's say if you have a cobalt and then you apply a magnetic field. And so this cobalt here has a spin. So let's say it has a spin in this direction, which means that you could actually write it down as a direction in this direction. So it turns out that the radiation from this cobalt mostly goes in the opposite way of the magnetic field. But if you do the mirror, what you observe is that first the magnetic field should be in the opposite direction, but also that the spin of the cobalt must be the same. The spin has to be the same direction. So when we do this, the result turns out that it will still go in this direction. And so this doesn't fully make sense. So it turns out that the symmetry behind physics is broken for very small things. But there are also observations that tells you that if you change your when you change your charge, your mirror as well as your time, this thing would be conserved. But this is out of the realm of what we'll be talking about in this video. So I won't fully discuss much about it anyways. So there are some people who are very interested in the patterns of the universe, and one of the ways that some people do it is by observing its eightfold way pattern. So this is a pattern in which if I understand it properly, it's a hexagon in which each of these hexagon corresponds to certain properties, as well as there are two different particles in the center here. And so each of these coordinates here corresponds to certain strangeness, certain spins, and etc. But I won't fully discuss much about it because I don't fully understand about it. But something from this observation tells researchers that there are particles in which they are fundamental that builds up all of the other things. And this is what we call as the standard model. To talk about the standard model, what we need to understand first is the quarks. So quarks are the elementary particles, and there are lots of these, and the most popular ones are the up and the down, which forms the proton and the neutron. And also there is the strange quark, which is the one that governs strangeness. And each of these also has their antimatter counterpart. So the up quark and the down quark has a 2/3 elementary charge and a negative 1/3 elementary charge. And so if you try to build it up into baryons, like the proton and neutron, they would be positive. They would be up, down, and up, down, down. So it turns out that there's a triad, and a triad corresponds to a baryon. So if you have a triplet of quarks, that means that it will be a baryon. And so the main reason of this is that baryons are the one which has a odd integer spin. And it turns out that quarks have integer spins. So we don't need to care much about if it is oddly integered. As long as it's a baryon, which means that it's a multiple of 3, it would form the baryon, or technically a odd multiple. But But if you have this to be a pair, this is what we call as the meson. Some examples include the interaction between up and the anti-up. And so this thing has a spin of 0, which is a integer. So this is what we call as the meson. So technically anything which is a even multiple corresponds to a meson. So since there is something which we have this up down relation to be, and each have their own same quantum number because they are describing one set of this proton or the neutron, there has to be something that's different. And so this different quantum number is something which we call as the color of the quark. So the color of the quark isn't really a color, but it is a way for it to describe charge. And so there are 3 types of these charges: red, green, and blue, which is not really the color. And so this theory is something which we call as the quantum chromodynamics. And the interaction between these colors is governed by the gluon, in which there are 8 different types, which corresponds to the 6 color pairs, and the 2 colorless pairs. So this interaction governs your strong force, it turns out. So from this interaction, what we'll later observe is that it turns out that every single particle that is something that we could actually observe are always colorless. Particles are always colorless. And this is because of the interaction of the gluon. The gluon doesn't care about distance. So you could have something that is very close by or something very, very far apart, and it is still the same gluon. It doesn't matter about how far this interaction is. So now we could start to talk about the standard model. So what's the standard model now? So the standard model consists of all of the elementary particles that we already know currently. So it is normally grouped as this. First we have the quarks, which is here, and then you got the leptons, which is here, and so these are the fermions, and then on the right hand side are the bosons, which include the 4 interacting ones and one special one which we call as the Higgs field or the Higgs boson. And this Higgs boson determines your mass of each of the particles. So the quarks, there exists the up quark and the down quark. There's also the charmed and the strange. There's also the top and the bottom. So the top one here has charge of 2/3 electrons, and the bottom one has charge of -1/3 electrons. For the leptons, these include the electron, the muon, and the tau, as well as the neutrino, sorry. And then for the bosons, you would have the gluon, the photon, the Z particle, the Z boson, and the W boson. So the W boson has 2 different flavors, the positive one and the negative one. And so each of these things here has their antimatter counterpart. So it turns out that the standard model only determines the things which are actual matter, not really the antimatter. So the standard model tries to unify every single particles that we know, such as the forces. And so there's a equation in which most physicists dream to solve, which is the unification. And so the unification starts from the electromagnetism as well as the weak force. And it turns out that you could combine them into one single equation called the electroweak force. And then after that, you could try to implement your strong force, and this generalization turns into the equation of the grand unification. but we haven't combined gravity yet. So if we have already studied gravity well enough, and some physicists developed equations of this, we would get the unification of the entire forces, and one explanation of this is from string theory. So string theory pretty much tells you that you just imagine particles to be wave functions. And so these wave functions are imagined as something like strings in which they vibrate within their own resonant frequency, and this determines what particle is what. So when we have gone from this very small quanta or this very small scale into this very large scale of generalization, so we can finally discuss about the universe itself. And so the universe was the universe was observed to be expanding, in which the expansion was determined by the Hubble's law, V equals to h0d, in which h0 is the Hubble constant. The value is 22 kilometers per second per million light years. And so this equation tells you one thing, that the universe is stretching. So so if the distance is very small, it doesn't feel that much stretching. But if you go to somewhere very far, you would see larger stretchings in the form of the Doppler effect. And so this idea of the universe stretching tells you about a very cool theory, which is the Big Bang theory. And so this is just a theory, it is not really proven yet, but it might be the origin of the universe. And not only that the universe stretching is the main conclusion of the Big Bang, but another conclusion is the cosmic background radiation. Background radiation. And so this radiation comes from the photons wandering around space. Wandering around space. So observing such photons actually tells you that at the early universe, the universe was very hot to the point where photons are generated, and then because of this expansion as well, the universe starts to cool, but this radiation is still propagated throughout space. And so this is why we have this cosmic background radiation. So this radiation here tells you about the very hot universe. And so because of this very hot universe, this is where charged particles exist by itself. Charged particles exist. And not only that, once it cooled by a bit, you could form the nucleus. And then after that, when it is much more cooler, electrons could fill in to form your atoms. And so from these atoms, there are interactions of gravity as well as the nuclear force, which will pretty much tells you about fusion, which creates the stars to create much more bigger atoms. So there is a very recent discovery, not really that recent, I believe it's at 2015, but there is someone whose name is Gut, and with his theory, he determines that the universe was not only expanding linearly, but it is expanding exponentially. And so this exponential increase is something which we call as a inflation. So this inflationary universe is the new knowledge that we have received until now. And so there are much more further studies about the origin of the universe. You could try to use your Newton's law to develop the density of the universe. So if you try to figure out, does the universe will expand always? What you would need to know is the ratio of the kinetic energy over the potential energy. And so if this is greater than 1, what it means is that your kinetic energy will dominate, which means that it will expand further and further. But if the potential is greater, this means that we have a limit of this expansion. And so from the Newton's law, you could determine the density of the universe, and this is obtained to be 3h0 squared over 8 pi g, in which g is your gravitational constant. Now, if you try to compute this density, it turns out that the universe itself, the one that is consisting of matter and antimatter, doesn't 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 give you the density of the universe that we know now, thanks to the observation of the expanding universe from time to time. So so this so this realization tells you about that there is something which we call as a dark matter. So what dark matter is that it is matter in which we couldn't truly observe. It is something that we don't observe within within our everyday life. You normally see dark matter when you're dealing with with astronomy. So it is not something that is very theoretical, but it exists, but we don't know what dark matter actually is. And so this is why we actually try to figure out what type of property does dark matter have? What type of interaction does it have with regular matter? But thanks to this dark matter in itself tells you about the expanding universe. And this expanding universe tells you that from this dark matter is the source of this dark energy. And so this is the summary of entire physics, starting from classical mechanics until electromagnetism, and then we wander into the realm of modern physics, in which we talk about quantum as well as relativistic physics. And all of this combined forms the idea of particle theory until cosmology. So this is where I'm going to leave it for now for this entire discussion of general physics 2. And so the next series will be covering about electromagnetism, and probably we will also be talking about some classical mechanics or maybe even material science. But anyways, this is the end of the video as well as the series on general physics 2. So thank you very much for watching. Make sure to like and subscribe, and also please share this to your friends who really needs to understand physics in a much more deeper understanding. Thank you very much, and I will see you on the next video.